Our next speaker is going to tell us about mathematical truth, and we are going to go from ideal to the necessity of infinity.
Okay. I'd like to thank the organizers, an unusual meeting. So I'm going to talk about very current issues in my area of mathematics, which is set theory. As well known, we have the limits of proof. There's the Gödel theorem, Gödel-Rosser theorem, that if mathematics is free of contradiction, then there's a formal question of mathematics whose answer cannot be deduced on the basis of the axioms. And then there's a companion theorem. If mathematics is free from contradiction, then mathematics cannot prove that mathematics is free from contradiction. So I want to give a more modern view of these theorems to emphasize a different perspective of them. It involves a Turing machine. So let me remind you. So the questions are, these are practical concerns. Well, I guess if mathematics was contradictory, that would be an issue. But is there any likelihood of that? Okay, Turing machine. So this is an idealized, simplistic computer. The mechanics, you have an infinite tape partitioned into squares. Each square contains the symbol 0 or 1. There's a scanning head, which is positioned on some square. There are the software components of the Turing machine. The Turing machine has a finite number of active states, say S1 up to Sn, and one additional halting state. And then there's a program. And the program specifies the action based on the situation of the machine. So we have to look at what that means. So what's the situation of an active Turing machine? Well, it's the symbol in the current scanned square. So there are two possibilities. Remember, every square has either a 0 or 1. And then there's the active state of the Turing machine. Which state is it in of those n states? Now, what are the possible actions? Well, the scanning head can write either 0 or 1 in the current scanned square. Then the scanning head moves either 1 square to the left or 1 square to the right. And then the Turing machine enters a specified active state, or it enters the halting state and it's no longer active. An incredibly simplistic model of computation. If you just count them up, there are 2n many possible active situations, what's in the scanned square and then active states. And then there are 4 times n plus 1 many possible actions. So there are only 4n plus 4 raised to the power of 2n possible programs for a Turing machine with n active states. All right, so we can use this to define a notion of simplicity for numbers. An integer k bigger than 0 is n simple if there's a Turing machine with n active states and program p, such that if it starts on the tape in which 0 is written in every single square, it eventually halts, so enters the halting state, and when the machine halts, the symbol 1 is written in exactly k many squares, and the scanning head is positioned at the leftmost square with 1. Okay, so a very simple way a Turing machine might calculate an integer. Well, so we just counted up how many possible n-state programs there are. So there are at most 4n plus 4 raised to the 2n power 2n many n simple numbers. And that's not a very good estimate. It's just an upper bound. All right, so you can play around with this. 1 is 1 simple. That's easy. It's the only 1 simple number. 2 is too simple, and 2 is the only too simple number besides 1. As I said, there are at most 4n plus 4 to the 2n many n simple numbers. So let's take n to be a billion, 10 billion. And consider the infinite sequence of statements. 1 is not 10 to the 10 simple. 2 is not 10 to the 10 simple. Those are both false. ... k is not 10 to the 10 simple. So we have an infinite number of statements. And we know that all but a very small number of them are true. Because we know how many, we have an upper bound for how many 10 to the 10 simple numbers there are. So no one's going to question that. No finitist question that. Okay, so they're at most, I'll bring in a Googleplex, many 10 to the 10 simple numbers. So all but at most a Googleplex of these statements are true. And that's a Googleplex is much larger than the bound that I just gave. Well, after Chaitin, if mathematics is free from contradiction, mathematics cannot prove any of these statements, not a single one. If you increase n from 10 billion to a Googleplex, then this is for any system of mathematics that can be written down in our physical universe. So we have a knob here, it's just how big you make n, and we can quickly get to statements, an infinite number of statements. We know all but a small number of them are true. Can't prove a single one. So that's a little stronger philosophically than the Gödel-Rosser theorem. Notice there's no notion of proof here. There's no self-reference. There's no, I'm not talking about which system, just a very informal fact written down. Look at any journal ever written. Okay, so, and, okay. Now you can actually get, and this was an observation of about 10 years ago, the second Gödel incompleteness theorem the same way. So let's take K to be at most a Googleplex. Suppose mathematics proves there are at most K many 10 to the 10 simple numbers. Well, we already know that's true if K is equal to a Googleplex. Now suppose there are K many 10 to the 10 simple numbers. And mathematics is inconsistent. And this is true for any system of mathematics ever written down. Well, now we have the second incompleteness theorem. If mathematics is free from contradiction, then mathematics cannot prove that mathematics is free from contradiction. Well, why? Suppose it could. Well, you'd start with a Googleplex. We know there are at most a Googleplex of many 10 to the 10 simple numbers. But there can't be 10 to that many, because then mathematics will be inconsistent. So we just proved there's a Googleplex minus 1 as the upper bound. And now just repeat that argument a Googleplex number of times, and you have a contradiction. You just keep subtracting 1. These are specific numbers. You know, a Googleplex is a specific finite number. It's very big, but it doesn't matter. So this view using Kolmogorov complexity, that's what this really is, gets you both incompleteness theorems, but in a more profound way. Hard to disregard them. I mean, the Gödel, if you're a finitist and I say number theory, the formal theory of number theory, whether it's consistent or not, you can't prove it. Finitist said, why should I care? Or do it this way. Take the, for those of you who are familiar with it, take the Gödel-Rosser sentence. Suppose that piano arithmetic is inconsistent. You don't know whether the Gödel-Rosser sentence is either true or false. So the the meaning of the Gödel-Rosser sentence, whether seems to hinge on whether or not the formal axioms for arithmetic are consistent with finitist and empiric. All right. So what's the ultimate mathematical universe? Well, I'm a set theorist. So it's V, the universe of sets. And all the objects of mathematics are in V. And we sharpen our conception of V by the formal ZFC axioms. One cannot use the ZFC axioms to prove any of those statements. K is not 10 to the 10 simple, unless these axioms lead to a contradiction. Maybe this is all evidence we should just reject mathematical infinity, and perhaps even reject potential mathematical infinity. So do we really need infinity? All right, so let's look at the classical incarnations of infinity. We have formal number theory, the piano axioms. The objects are the natural numbers, 1, 2, 3, ... Set theorists like to be controversial and start with 0. We have the formal axioms of number theory, the algebra axioms, those that you would write down. And then we have the induction axioms, which are a scheme. And they just say if you have a formal property of numbers, and there are numbers with that property, there's at least one. So the question is all of mathematics in essence just a study of the formal consequences of PA? Independent of how we visualize it. Is that all that's going on? Well, if that's true, where does that leave infinity? Now, if we take one step beyond number theory toward set theory, we get second order number theory. So what are the objects here? They are the natural numbers, the objects of number theory, together with all sets of natural numbers. What are the formal axioms? The algebra axiom, same. The induction axiom is now just a single statement. Every non-empty set of numbers has a least element, but you don't escape having an infinite number of axioms because you need axioms that tell you that sets exist. And those are the comprehension axioms. And it's for every formal property P, the set of numbers with that property exists. So that's that gets you lots of sets. So we have two fundamental structures, arguably, of classical mathematics: the integers with plus and times, and then the standard structure for second order number theory. Okay, so one of the most famous theorems of the last 50 years is Fermat's last theorem, proved by Wiles. Suppose n is bigger than 2, then for all natural numbers, x, y, and z, x to the n plus y to the n doesn't equal z to the n. If you actually look at Wiles' proof in the annals of mathematics, it's not even a ZFC proof. He uses things, Grothendieck towers, that are not formalizable in ZFC. Right. They're not provable, right? Yeah. Okay, so the question becomes, can you prove Wiles' theorem in just PA? The statement of PA. Okay, so I'm dropping all the way down to PA. I'm not even going to allow second order number theory. So this has been looked at, and there are claims that one can. There are claims that you can do it, but it's a tedious exercise with no utility. Okay, I want to claim controversially that's not the right question. So let's go to finite number theory. Now, this is not an area that exists. Okay, so finite number theory, we'll call it FPA, F for finite. The objects are the natural numbers starting with 1 up to some largest number that is not specified, like the physical universe, if it's finite. Okay, we have the algebra axioms, but I'm not doing arithmetic mod n. So plus and times are partial functions. And so you just write down the obvious axioms. What about the induction axiom? Well, there are two ways of doing it, and they're not known to be equivalent. So I'm going to choose a pigeonhole principle. If you have a formal property, a function which is defined by a formal property, then the following are equivalent. The function is one-to-one, and the function is a surjection. Pigeonhole. So the other way to state the induction axiom would be the formal property of numbers, there's at least one. So this implies that it's not known within the context of FPFA whether they're equivalent. Okay, so what can you do in FPA? Well, so for every natural number n, we get the standard model of FPFA, whose largest number is n. And the simplest model has only one object, 1. Curiously, you can formalize logic in FPA, and you can show that FPA proves its own consistency, but not so interesting. Okay, let's work in FPA. It's kind of amusing. So you can define exponentiation as a partial function in FPA. You have to break down the exponents. Remember, you don't have much room to work, but it works. So Fermat's last theorem is a formal statement of FPA. Can Weyl's theorem be proved in FPA? If the answer is yes, infinity plays no role, even potential infinity, in Weyl's proof. You can't do asymptotics in finite arithmetic. You can't do any global methods. You have to get down in the trenches and do nitty-gritty calculations. The Riemann hypothesis can be formulated in FPA. In fact, almost all of the famous open problems of number theory have coincidentally already been refined to problems in FPA because they bring in estimates. So, and the FPA perspective naturally generates many new questions. So I'm not promoting starting a subject, I'm just pointing it out. But you could ask, is all of mathematics in the end just the study of the formal consequences of FPA? Well, if that's true, where does it leave us? Let me give you a simple example. Euclid's theorem that there are infinitely many prime numbers makes no sense in FPA. But Bertrand's postulate does. So Bertrand's postulate is that for every integer greater than or equal to 2, there's a prime number between n and 2n. Now, clearly, if you know that theorem, you know there are infinitely many primes. If you know, you can prove this. But this statement makes perfect sense in FPA.
But in the end, we have double.
Yeah. That's Bertrand's postulate. It was proved in the late 1800s by Chebyshev.
It means there's 2n existing.
I'm sorry?
You have to assume. Yeah.
Well, this in FPA, you may not have 2n, but you may, maybe my largest number is 2 times a googolplex. So I divide that largest number by 2. Is there a prime number in between? Well, yes, you can verify that. So does FPA prove that if 2n exists, that there's a prime number between n and 2n? I'm not saying n is the largest number. So if you look at Erdosh's proof of Bertrand's postulate, the so-called book proof, it probably proves this lemma. Suppose n is bigger than or equal to 2, and 2 to the n exists. Then there's a prime number between n and 2n. There's just, looks like if 2 to the n exists, there's enough room to do the sums that Erdos needs to do and prove that there's a prime. But if 2n is the largest number, there's no room to implement Erdős's proof. So it's not at all clear that FPA proves Bertrand's postulate. That if you have a number such that 2n exists, then there is a prime number between n and 2n. Might have to be a completely different proof. All right. Ramsey's theorem. Suppose n is a natural number. We'll say that a set X is an n set if X has exactly n elements. So a 1 set has only 1 element, a 2 set has only 2 elements. For each set Y and each natural number n, I'll use this notation to denote the collection of all n sets from Y. So these are all the subsets of Y with exactly n elements. Of course, if Y doesn't have at least n elements, this is empty. So there's Ramsey's theorem. For every natural number n, and for each natural number k bigger than n, there exists, too many quantifiers, a natural number m, so that if you color the n sets from 1 up to m with n colors, you can find a k set, all of whose n sets are colored the same. So if you've seen this, you know it. If you haven't seen it, don't worry about it. I'll strip off a quantifier. So Erdos numbers. So instead of coloring n sets, we'll color 2 sets. So n is 2. For each number k bigger than 2, we'll let E for Erdos, E sub k, be the least m that Ramsey's theorem tells us exists for 2. So that if you color the 2 sets from 1 up to m with 2 colors, you get a k set or a clique, all of whose two subsets are colored the same. So it's kind of like how many people do you have to invite to the party so that you have a k group of mutual acquaintances or mutual strangers. The coloring is stranger or not. So you can try to calculate these numbers. So E4 is 18. E5 is greater than or equal to 43 or less than or equal to 48. E6 is somewhere between 102 and 165. Okay, so there's the provocative conjecture of Erdos told in the form of a story that it's beyond human capability to determine the value of E6. You're never going to know. It's well defined. There's just too many things to look at. That's a dangerous conjecture, but he made that. Okay, but we can move into the infinite, and there's the infinite Ramsey theorem. So we're going to color n sets of all integers with n colors. And then there's an infinite set of integers, all of whose n sets are colored the same. So that's much easier to parse. Okay. Ramsey's theorem is proved in piano arithmetic. The stronger version makes no sense. And Ramsey's theorem, there's a stronger version of Ramsey's theorem that you can prove in FPA. The infinite Ramsey theorem makes no sense in arithmetic. You prove it in second order. Okay, the reason I'm bringing this up is we can miniaturize the infinite Ramsey theorem and get an interesting statement. This is the Paris-Harrington theorem. So for every starts out just like Ramsey's theorem. For every natural number n, there is a natural number m. Take any coloring of the n sets with n colors. Then you can find a set, all of whose n sets are colored the same. Okay, it has to have at least n elements, otherwise it's trivial. But we don't say how big it is. We say it has more elements than its least element. Notice we couple into the order. Okay. So if we took n to be 2, we would be looking for a number m so that no matter how you color the two sets of M objects, one up to M, you can find a set, all of whose two sets are colored the same, and you just want it to have as more elements than its least member. So if you try, if you don't put one in the set or two in the set or three in the set, suddenly the A has to start getting bigger. But that makes it harder to find the A. So maybe you can't have 4 and 5, and then it has to get bigger still. So there's a feedback there. So it's an amusing exercise that the Paris-Harrington theorem follows easily from the infinite Ramsey theorem, because an infinite set has more elements than its least element. So you can use a routine compactness argument. So in second order number theory, the Paris-Harrington theorem is true. Paris-Harrington showed that you can't prove the Paris-Harrington theorem in PA. So you make this slight change on the Ramsey theorem, and you get a more elegant theorem that PA cannot prove. All right, so this suggests we should define some numbers. So and these would be analogous to the Erdos numbers. For every n, PHn is the smallest m which witnesses the Paris-Harrington theorem for that n. Okay, so it's very analogous to the Erdos numbers. Those were the smallest numbers witnessing the Ramsey theorem, where n was 2 and k and so forth. These numbers, because this cannot be proved in arithmetic, what's really going on is these numbers are incredibly large. Even PH10, actually PH5, but I'm being conservative, PH10 cannot be written in decimal notation in arguments, even if you allow exponentiation as a shorthand. PH11 is vastly larger than PH10. So what's happening is, in fact, if you look at PH10, you can prove in arithmetic that PH10 exists. So well, you might say, well, what's the big deal then? Oh, wait a minute. What about PH sub PH10? We know PH10 exists, that's the number n. What about Paris-Harrington sub that number? You can't prove that number exists from PA by any proof of length less than PH10. So if you just iterate on the Paris-Harrington numbers, your PA can't, it's beyond human capability in this universe to prove those numbers exist. Well, how do we know they're not a contradictory conception? If we can't prove that PH sub PH10 exists, maybe we should be skeptical about it. Maybe this is the first crack in the door against infinity. Well, the way you deal with this is by Gödel sentences. So there's a formula in the language of FPFA that asserts that the Paris-Harrington number X, the Paris-Harrington number exists for a specific input. And so what the formula says is there exists y such that y is pH sub x, and then you have to give yourself enough room to certify. So you add a few exponentials. So there's a formula that we can use to interpret in the language of FPA whether a specific Paris-Harrington number exists or not. Nothing deep here. So you can now write down a Gödel sentence in the language of FPA. It's a sentence you could actually write down, small length. We'll call it theta sub g, g for Gödel. And what it expresses is that there's a proof of my negation from FPA of length less than PH10, that really big number. But then we add a wrinkle. It also asserts that pH 100 exists. So there's a proof, not so, well, very long, but it's saying two things. You can write the sentence down. Well, if you assume PA, not theta G, is true, otherwise PA is inconsistent, I mean, much worse. And you can also prove that there's a formal proof of not theta G from FPA of length less than pH 11. Remember, theta G says there's a proof of my negation of length less than pH 10. Well, you can have a proof of length less than pH 11, but that's not a contradiction. How can we be certain that there is no proof of not theta G from FPA of length less than pH 10? Well, what if there were a proof? Well, then pH 100 is an inconsistent conception. That wipes out all of mathematics. Nothing survives that. You get a nice corollary. You probably could prove Wiles from FPA because we don't have to do so many cases, but okay. So through the lens of FPA, why should these be a consistent notion? It's only through the lens of well, it's not even really PA, but well, for these it is. PA can prove accessibly that pH 100 exists. You can write it down, and it's not too long. So how can we secure the finite? Well, there's no proof of not theta G from FPA of we need to know this. But it's the theorem of PA. That's not helping us. Why does it imply there's no proof of not theta G from FPA of length less than pH 10? There's one from PA. Maybe if we were just clever, we could shorten the proof. But that would give us a contradiction. Well, in FPA plus pH 101 exists, then there's no proof from FPA of length less than pH 10. It's not helping. Why? Because why should pH 101 be a consistent notion? How do we know we can't find by any physical or mathematical means a proof of not theta G from FPA of length less than 10 to the 24th? Maybe the ultimate quantum computer could guess it and verify it. Or we can't, how do we know we can't find accessible and verifiable evidence which converts to a proof of not theta G from FPA of length less than pH 10? Maybe I have my 10 to the 24th quantum coins, I flip them. If quantum mechanics is absolutely correct, I have a non-zero chance of just finding that proof. How do I know I won't find it? Or maybe there's a way of steering, you can go on and on. Well, one way to secure the finite is to secure the infinite. So let's go back. So the simplest setting for the study of infinite is arguably second order number theory. We have the axioms. Can we answer the basic questions of second order number theory using these axioms, build a coherent theory, and thereby show that the conception of arbitrary sets of natural numbers makes sense, that's not vacuous, and then we don't have to worry about these finite sentences of Armageddon. Okay, so let's start on the journey. So the standard structure for second order number theory is P of n plus times epsilon. You have to know which integers are in which sets. It's really the structure of the real numbers with plus and times, together with a collection of simply defined sets of real numbers. These are called the projective sets of real numbers, not projective in the sense of algebraic geometry. Two ways to do it. You can look at the structure. You can do it logically. So you look at the logical structure P of n plus times epsilon. In other words, the reals with plus and times together with the natural numbers as a predicate, and do logical definability from parameters. That would be the logician's way. But you can also do this with calculus. So let's look at all sets of real numbers that can be generated from the initial set R of all real numbers in finitely many steps. The operations are you're allowed to complement, trivial. The second is from calculus, from a set X and a function from reals to reals, which is continuous when restricted to the space of irrational numbers. You can take the range of the function on X. That's the second one. We'll complement in that. Okay. So now what we can do is take famous problems in the context of set theory and localize them to the projective sets. Well, there's a projective axiom of choice. So what I'm going to do is reduce the axiom of choice. So you can define the projective subsets of the plane R cross R in exactly the two equivalent ways. So I can talk about functions that are projective, relations that are projective. Suppose you have a subset of the plane in X and it's projective. Suppose that for every real number R, there is a real number S such that the pair RS is an X. In other words, there's a fiber, all the vertical fibers touch the set X. Then there exists a projective set contained in X, which picks exactly one point. So if you have an R index family of non-empty sets of reals, there's a projective function that picks one point from each. But you can do it by a picture in the plane. You have the set in plane, and you're trying to fit the graph of a function inside the set, but you're requiring that that function be projective, which makes sense because we've defined projective subsets of the plane. So we're taking the classical notion of the axiom of choice and restricting the domain of consideration to a very tiny fragment of the universe of sets, the projective sets. Well, we can do the same with the continuum hypothesis. So recall the continuum hypothesis is the assertion, Cantor's continuum hypothesis that, sorry, I'm not supposed to walk, that if you have an infinite set of real numbers, it's either equinumerous with the natural numbers or equinumerous with the real numbers. Well, we can just take that statement and projectify it. Okay, so suppose X contained in R is an infinite projective set, then the projective continuum hypothesis asserts that either there's a bijection, a projective bijection of the natural numbers with X, or there's a projective bijection of the real numbers with X. So we have taken the continuum hypothesis and the full abstraction of the universe of sets, and we're restricting it to the projective sets. So now we have two natural questions about the projective sets. And by 1925, these had been classically considered. By 1925, Luzin conjectured these were hopeless problems. Never be solved. Like Erdős's prediction that we'll never know E6. Well, it's amazing. They are unsolvable. Both the problems given by the projective axiom of choice and the projective continuum hypothesis are formally unsolvable on the basis of second-order number theory. In fact, they are unsolvable within the ZFC axioms of set theory. Now, I guess I should have said, well, why were these questions about the projective sets questions of second-order number theory? Well, remember the first way I defined the projective sets was logical definability in P of n. So the projective sets are definable classes in second-order number theory. And so these, in some sense, are questions of second-order number theory. And in fact, the two universes that Gödel and Cohen constructed demonstrate this. Gödel's construction of his L, the projective axiom of choice and the projective continuum hypothesis both held there. And in Cohen's enlargement by his revolutionary method of forcing of L both fail. Maybe not all's lost, though. Maybe all we have to do is sharpen our conception to find the answers. So let's introduce the notion of a projective frame. Projective frame is an extension of the formal axioms of second-order number theory that provides a complete description, and I'll be vague about that. The extension should be specified by a specific recursive set of formal axioms. The extension should be consistent with the axioms of set theory. And what does complete mean? The extension should be immune to Cohen's method for showing that problems are unsolvable. So if you're in a universe of sets and you have the projective frame and you apply Cohen's method, you don't change the frame. You can change what numbers exist, real numbers. I'm being vague because I don't want to make bore you with many definitions. So there's the Gödel frame. I'll call it, it's the projective frame Gödel given by Gödel's axiom, V is equal to L for the universe of sets. The Gödel frame implies both the projective continuum hypothesis and the projective axiom of choice. But there are other frames. In the early 60s, an alternative to the axiom of choice was introduced, the so-called axiom of determinacy. That's not determinacy as opposed to determinacy and free will, more of games. So there's a projective frame given by that axiom. We'll call that the PD frame, PD for projective determinacy. Davis showed that the PD frame implies the projective continuum hypothesis. Moskowakis showed that the PD frame implies the projective axiom of choice. So we have the Gödel frame, we have the PD frame. But we can strengthen the projective continuum hypothesis to the strong projective continuum hypothesis. And that asserts that if you have an infinite projective set and it's not countable, then it contains an uncountable closed set. Closed sets are projective. The strong projective continuum hypothesis implies the projective continuum hypothesis, but they are not equivalent statements. So the strong projective continuum hypothesis kind of tells you why the projective continuum hypothesis is true. It's a classical theorem that if you have an uncountable closed set, it has to be equinumerous with the reals by a projective function. I should have said that. Well, you can also strengthen the axiom of choice to the projective well-ordering principle. So the projective well-ordering principle asserts that there's a well-ordering of the reals that's projective. Okay, so again, the well-ordering principle is key in set theory, and we're just localizing it. The projective well-ordering principle refutes the strong projective continuum hypothesis. And it's just projectifying the proof that if the reals can be well-ordered, there's an uncountable set of reals that doesn't contain an uncountable closed set. So you can take classical argument and kind of localize them into the projective domain. So now it turns out we have divergent projective frames. In the Gödel frame, the projective well-ordering principle holds. That's why the projective axiom of choice holds in the Gödel frame. In the PD frame, the strong projective continuum hypothesis holds. That's why the projective continuum hypothesis holds in the PD frame. So the projective well-ordering principle does not hold in the PD frame. So there's a whole mathematical story here. How is it you get the projective axiom of choice without having the projective well-ordering principle? And that comes from a deep analysis of the projective sets in the context of PD. In fact, there's a bewildering array of divergent projective frames. All kinds of projective frames. We're not making any progress. Except there was a hint for the 25 years after Cohen's discovery of forcing the PD frame remained the only projective frame in which both the projective axiom of choice holds and the strong projective continuum hypothesis holds. There was only one example known, and that was the PD frame. And so a conjecture emerged that the PD frame is the only PD frame where you have both a projective axiom of choice and the strong projective continuum hypothesis. So that starting to look like maybe there's something promising happening. But then a new class of projective frames was discovered, in which the strong projective continuum hypothesis holds, the PD frame is false, and the projective axiom of choice holds. The conjecture is false. So it's looking like the attempt to understand second-order number theory is just completely failing. To succeed, it would have to identify the one true projective frame. And every time we look like we're making progress, things fall apart. We're stuck with a multiverse of projective frames. What about the V perspective? The axiom that there's a measurable cardinal is a fundamental large cardinal axiom. And Robot in 64, 60 years ago, showed that if there's a measurable cardinal, the Gödel frame is false. The conception of V, the universe of sets, entails rejecting the Gödel frame, because V is supposed to have everything in it, all large cardinals. What about the other projective frames? Well, there was an unexpected and perfect alignment. Almost 40 years ago, Martin and Steele showed that if there are infinitely many Woodin cardinals, and I won't bore you with the definition, then the PD frame holds. So I'd shown earlier that the strong projective continuum hypothesis held and other things from this. But in fact, we can now say the PD frame is the one true frame. The PD frame is equivalent to the theory of second-order number theory given by the ZFC axioms, together with the axioms there are n many Woodin cardinals as a scheme on n. So infinity forces the PD frame to be true. That's the Martin-Steele theorem. But you get a perfect alignment. You know exactly how to calibrate the PD frame in terms of infinity notions. So that looks pretty good. And out of that comes a new truth of FPA. The PD frame is consistent, which wasn't at all obvious. So that's a new claim. That's a new falsifiable claim that the PD frame is not contradictory. And you can't prove it from set theory. You can't prove it. There's no way, there's no plausible way to justify this falsifiable claim other than the conception of the universe of sets in which there are Woodin cardinals. In other words, in which the PD frame is true. No one has come up with another explanation so far. So I will make a prediction. I said this is a falsifiable claim. So I'm going to make a prediction about the real world. This claim won't be falsified by the 1000th anniversary of this conference. Now, that is a prediction about this universe. What? Well, maybe if the biologists help, yes. Or you go to sleep for 1,000 years. Yeah. So I throw this out to the physicists who claim there's going to be an ultimate physical theory that's supposed to prove all aspects of the universe. This claim is an aspect of the universe. How is this ultimate physical theory going to prove this claim? Without waiting. All right, I'm almost done. But we have to be serious now. Has this success secured the infinite? The PD frame is secured by the conception of V, but we've now changed the scope from second order number theory to V. Well, doesn't this demand that we transition from projective frames to V frames? Otherwise, it seems dishonest. So you could ask, is there an expansion of the ZFC axioms which yields a conception of the universe of sets, immune to Cohen's method, compatible with all large cardinals? In other words, we want a V frame. We want the generalization of the PD frame to V. Up to about 15 years ago, this seemed completely hopeless. But by generalizing the projective sets to a vastly larger collection of sets of reals, one has naturally led to a generalization of the PD frame. This is not a generalization of determinacy. To a single axiom, V is ultimate L. It's a specific formal axiom for the universe of sets. This axiom settles the problem of the continuum hypothesis and much more. It implies PD. The axiom yields a V frame which is immune to Cohen's method. So the trouble in set theory now is Cohen's method is so powerful. You write down a statement of set theory that you want to study, and chances are you can't prove or refute it. And enormous effort has been devoted over the last 60 years to refining Cohen's method, an incredibly powerful technique for manipulating universes of set theory to understand what can or cannot be proved. And it's very rare that you find something that can be proved. The conception of the universe of sets just doesn't seem to be a rigid conception. V is ultimate L removes Cohen's method. You cannot use Cohen's method. So the only ambiguities about the universe of sets in the context of V is ultimate L is the height of the universe. What infinities exist? And that was a dream of Gödel. But is V the ultimate L the one true axiom? Does it pass the large cardinal test? The axiom, Gödel's axiom, V is equal to L, yields a V frame, immune to Cohen's method, but it doesn't survive the large cardinal test, so we have to reject it. Now we have a new version of V is equal to L. V is ultimate L. But now that axiom couples into a whole nother area of set theory, and so that's how we're able to prove CH and things like that from this axiom. And it's how we're able to show that this axiom is immune to Cohen's method. Okay, so the large cardinal test, set theory at a crossroads. If you assume V is equal to L, there are no measurable cardinals. Gödel's axiom fails the large cardinal test. They're now a very specific set of conjectures. These are the ultimate L conjectures. These are precise, falsifiable statements, or verifiable, depending on which one. These conjectures, if true, these are number theoretic statements. So if you accept meaning, mathematical truth for the integers, these conjectures are either true or false. They are not conjectures about the universe of sets. They are conjectures that this theory proves this, or this theory is consistent. That's it. The ultimate L conjectures also, and I'll be controversial here, if true, provide compelling evidence that the axiom V is equal to L, ultimate L is the true missing axiom for set theory, and that we'll just dispense with this ambiguity that's been created by Cohen's method of forcing. The ultimate L conjectures are formally statements of number theory. I just said that. They must be true or false. They cannot be meaningless unless you're going to challenge truth in number theory. So we're really at a crossroads. We have this very specific axiom. We have these very specific conjectures. There's no reason to believe we don't have the tools. In fact, a lot of progress has been made towards proving these conjectures. That's an ongoing project now. It's not like we don't have any idea. And hopefully this is going to get sorted out one way or the other within the near future. So thank you.
Thank you so much. Now we have some time for questions. Yes, Michael?
Yes, that's the way. Good question. Do you use the heuristic version more to secure? What do you mean exactly?
Okay.
Secure.
So let's suppose that go back to that. There's a contradiction in FPA if you assume that pH, I don't care, 100 of it. That wipes out all of mathematics. There's just nothing survives. So we would like to secure ourselves against that possibility. Maybe the National Science Foundation should invest just a little bit of money, or maybe the government should, in trying to figure out whether we're going to have a collapse, because that would be a problem. So we would like to secure ourselves against that. Or let me draw an analogy. I want to build a very tall building, and I'm worried about the stability of the ground where I'm building it. Maybe we shouldn't have built this building here. Well, I could search out and try to show that it's bedrock in every direction out a long ways and secure that I have no doubt about the security of this building site. So the idea is, if there is a contradiction in the finite, then it should be easier to find the contradiction in the infinite. Now, the skeptic will say, it's going to involve such radical new ideas that makes no sense. But okay, let's grant that. But then the investigation of the infinite shouldn't succeed. See, one could take the view, and some logicians have, that the ubiquity of unsolvable problems in set theory is a symptom of the fact that it is meaningless. The set theory is entirely a human creation, and there's just no meaning. All right, maybe they say second order Zermelo set theory or whatever, but that's not an unreasonable position, I would say. We have a conception of the universe of sets, so we're not making much progress in figuring out what's true in that universe. We're making a lot of progress in what's possible to be true. That's not the same thing. If the conception of the universe of sets is a meaningful conception, CH has to be true or false in that. Can't be both true and false. So when I say secure, I would like to know that I'd like to be confident that the conception of the universe of sets is not a contradiction. It's not entirely, a puzzle that we've got, a game that we are playing. And I've encountered through my years just an attitude that mathematicians aren't concerned about a contradiction in their domain of mathematics because we'll define it away. It'll be, that axiom. We never use that axiom anyway. You don't define away a contradiction in FPA. That's impossible. And the fact that there is a form of the Gödel incompleteness theorem that makes perfect sense in FPA, I think is worth pointing out. It's a slippery slope. Where do you think questions have answers? Most of the mathematicians that I've encountered think that arithmetic statements are either true or false. The twin prime conjecture is either true or false. It's not, and that the conception of the integers is coherent, and these questions have answers. Well, all right, you're taking a position. I might move that goalpost a little further and say, well, I think the universe of sets or second order number theory is a coherent conception. or one might retreat. That's what I mean by secure. We all believe that some kernel of mathematics is free from contradiction. And it's just where you draw that line. Is it FPA with pH sub 1,000 exists or pH sub pH 10 exists? Is it PA? Is it second order number theory? Is it Zermelo set theory, which is much weaker than ZF? Is it ZF? But I would just point out, I mean, the theme of this conference is philosophy and mathematics. This entire line of investigation is philosophically driven. It's not calculation.
Right. This was my second question. Yeah. I perfectly agree with you. But it's very difficult for me to understand, not because we were not clear, but in general, what does it mean here, philosophy? So it seems to me that it's true. What you say seems difficult to translate. But at the same time, very difficult to well understand the problem.
Yeah, so what happens, at least in set theory, you could say, oh, I'm trying to figure out what's true about the universe of sets. What alternative conceptions of truth might there be? And does that lead to mathematical questions that I could answer that would constrain that conception? That's a very active and dynamic process. So the ultimate, all of that came out of just trying to see if there was a way of sharpening the conception of the universe of sense. And it led to a very interesting series of mathematical questions. You strip, take deep mind, chat, GPT, all of that. All right, are we the go masters of 100 years ago? I'm talking about we, the mathematicians. We have a skill set, we do things, we think we're not going to be replaced. Well, maybe super deep mind in 100 years ago can just prove all the theorems ever been proved from scratch, press a button. It has incredible capabilities. I'm not going to answer the continuum hypothesis. In fact, super deep mind, an oracle for arithmetic truth. That's not going to answer CH. So I'll leave you, because we're out of time, food awaits. So I hope I answered your question. I'll leave you with a question. Okay. You enter a great hall. It's the great hall of oracles, and they're doors. Okay. And you come to two doors. One is number theory, and one is set theory. You can only open one door. Okay, now what's going to happen? If number theory is meaningful, then you open the door, sitting behind the desk will be the oracle, and then you can ask 100 number theory questions and you'll be told the answers. If number theory is not meaningful, the room is empty. Same for set theory. Which door will you open? Hey. But why wouldn't, so that means, see, I'm a set theorist. I think set theory is meaningful. I'll open the set theory door. And the reason is, well, look, if that room is empty, I know how to spend my remaining years. And if that room is non-empty, I've just answered all the questions of number theory. So I'll get the 5 million remaining dollars in Millennial Prize. I'll get everything. Whereas if you open the number theory door, all right, you still get the 5 million, but you don't get any set theory answers. So you should open the door that gets you the most utility. Anyway, something to think about. Which door would you open? So thank you.
Thank you very much. This was really very, very, very interesting. I had my own reasons to believe that infinity exists with Gottstein sequences and the Hydra problem, but this is such a small infinity. You gave me many reasons to believe that many larger infinities exist. So thank you so much. Now we have about 15 to 20 minutes of coffee break. Maybe if we put our minds together, we could falsify the conjecture.
Okay.
That was predicted not to be falsified in how much?
1,000 years.
So we have 20 minutes to decide what are the problem.